Hey everyone, welcome to Discussion 1's walkthrough. My name is Varun and I'm one of the TAs for this course. I'll be focusing on Piazza, review sessions, and discussion walkthroughs. Let's go through question number 1. This question is on asymptotics and limits. In CS170, we care a lot about the runtime of algorithms. We don't really care about the performance of algorithms on small inputs. We really care about the bigger picture. That is, what happens to algorithmic performance as you increase input size. This is known as asymptotics. And in this worksheet, we'll be going through some limit rules to determine if a function is upper bounded by another function. So there are 3 rules here on this worksheet that come to mind and can be used in your algorithmic toolbox to determine if a function is upper bounded by another function, right? So let's look at the very first rule. If you take the limit of the ratio of the two functions as n approaches infinity, that limit should be equal to 0. If the limit is equal to a constant, then f of n is in theta g of n, that is, they grow at somewhat the same pace. And if the limit is equal to infinity, it means that g of n is actually upper bounded by f of n. Okay, so now using these mathematical definitions, let's actually walk through subparts A and D, subparts A through D. So our very first question is to prove that n cube is upper bounded by n to the fourth. That is, n to the fourth grows faster than n cube. So using the limit definitions that we saw previously above, let's define f of n to be n cube and g of n to be n to the 4. Let's take the limit of the ratio of these two functions as n approaches infinity. This again is equal to the limit as n approaches infinity of n cubed by n to the 4th. That's the limit as n approaches infinity of 1 over n. That's equal to 0, which by our definition above implies that n cubed is indeed upper bounded by n to the 4. So a small distinction here to notice is that this notation, big O n to the 4, is actually a set. So it is the set of all functions that are upper bounded by n to the 4. Now there are infinitely many functions that share this characteristic, and n cube is one of them, which is why if you're kind of picky about set notation, it would be more mathematically correct to say that n cube is a member of this set. However, for the purposes of this class, I think saying that they're equal should be just fine. Okay, now let's find two functions f of n and g of n such that f of n is upper bounded by g of n. However, the limit of the ratio of the two functions as n approaches infinity is not equal to 0. This is kind of a tricky question because we are looking to find two functions that are upper bounded, one of which is upper bounded by the other. However, we don't want to be able to use we don't want to be in a position to define that relationship by the limit, right? So let's think of an example here. Notice that saying that a function is upper bounded also means that it grows at the same pace. So this is the same as saying that f of n is also equal to theta g of n, right? Because if a function grows at the same pace as another one, it is also technically upper bounded by that other function. So let's use that definition here to our advantage. So let's say that we have a simple polynomial. Let's say f of n is equal to 3n and g of n is equal to 5n. In this case, the limit as n approaches infinity of f of n over g of n is equal to the limit as n approaches infinity of 3n over 5n, which is equal to 3 by 5, which is lesser than 1. In this case, this is the definition, that f of n belongs to theta g of n, and this implies that f of n belongs to big O g of n. That's how we get our big O definition right there. All right, so now the next question asks us to use L'Hopital's rule to show that log n is upper bounded by n to the c. So let's break out the limit. Limit n approaches infinity of f of n g of n is equal to the limit n approaches infinity of log n by n to the c. This takes an indeterminate form, so we apply L'Hopital's rule to differentiate, and we say that the limit as n approaches infinity of that expression is equal to the limit as n approaches infinity of 1 over n divided by c to the n c minus 1, which is equal to the limit as n approaches infinity of 1 over n to the c, which is equal to 0. And clearly here, this definition lets us conclude that log n is definitely big O into the c. Okay. In question D, we are asked to find two functions such that one is upper bounded by the other, yet the limit does not exist. So let's try and get a little creative here. So let's think about trigonometric functions. Because the second I see a limit doesn't exist, the first function that comes to mind is maybe a sine x. So let's think about how we can use that to define two functions here. So what if I had a function f of n is equal to x sine x plus 1, and g of n is equal to x, right? So I know that sine x plus 1 is always upper bounded by 2, because sine x is always upper bounded by 1, right? Now this by definition implies that right? So f of n is upper bounded by 2 times g of n for all x positive, which means that f of x is indeed big O g of x. Now if we try and evaluate the limit, we get limit of x sine x plus 1 divided by x as x approaches infinity. And this limit is undefined because sine x, that's probably the wrong notation, but the limit is undefined because as x approaches infinity, sine x doesn't converge. It oscillates forever, right? So that helps us conclude that f of x is indeed in big O g of x without having a limit definition. Awesome. So that concludes the walkthrough of question 1, and we'll move on to the walkthrough of question 2 in just a second. Hey everyone, welcome back to question 2 of discussion 1. We're going to go over asymptotic notation once again. So for these questions, we want to state whether f of n belongs to big O g of n, omega, or theta g of n. And we're sort of going to think about the rules we saw last time using limits in math to determine these relationships. So first of all, let's start off with question A. So we have two functions f of n and g of n. N squared grows faster than n. So here we can say that f of n belongs to big O g of n. Clearly because n squared grows faster than n. Second subpart, so both these functions have an n squared, n squared is the highest term, so these functions will both grow at roughly the same rate, right? So for this one, f of n would belong to theta g of n. Part 3, f of n equals 8n and g of n equals n log n. So I think for this question, a good rule to have in mind is if you have any positive constant c, we know that n to the c is always big O n to the c log n, right? And this is simply because log n is always greater than or equal to 1, right? So if we set c equal to 1 in this example, we get that n belongs to big O of n log n, right? So f of n equals 8n. 8n and n grow at almost the same rate, right? So we can say that f of n over here once again belongs to big O g of n. Part 4, we know that polynomial functions grow slower than exponential functions. Exponential functions tend to shoot up faster. So for this one, we can say that f of n belongs to omega g of n. For this question, let's simplify things a little bit. So we can say that g of n is equal to 4 to the n. So f of n divided by g of n, so the ratio of the two functions is going to be 3 by 4 raised to n. If we take the limit of this as n approaches infinity, 3 over 4 is smaller than 1. So any sort of number that's smaller than 1, if you raise it to an infinite power, this goes to 0. So the limit of this entire expression as n approaches infinity of all of that is going to go to 0, which means that f of n is big O g of n. Okay, now let's move on to the next question. So for these expressions or functions, we want to state the order of growth using theta notation, right? So we want to have an expression of the form f of n is equal to theta of some expression or some function, right? So f of n is equal to 50. Well, that's a constant number. So as we increase the size of n, the output is always going to be 50. So for this one, we can say that theta n belongs to, or sorry, you can say that f of n belongs to theta of 1. Part 2, in this polynomial, n squared is the highest term. So we can say f of n is theta of n squared. The sum of all the natural numbers from 1 to n is equal to n times n plus 1 over 2. This is some expression involving n squared. So once again, this entire thing belongs to theta of n squared. For part 4, we know that this base is bigger than 1. So as you increase its power, it's going to grow exponentially. So this entire thing is going to be theta 1.01 to the n, right? For part 5, n to the 1.1 is going to grow faster than n log n. So this entire expression is going to be theta of n to the 1.1, right? For part 5, that was for part 5. So for part 6, we have f of n is equal to g of n the whole square, where g of n is equal to root n plus 5. So let's actually expand this and see what we get. So we have a root n plus 5. And if we square that, we get an n plus 10 times root n plus 25. So this has two functions of n. This is an n to the 1. That's an n to the half. So and this n to the 1 is going to dominate. So this entire expression is going to be theta of n. The sort of trick here is that if you have n to the c, this belongs to theta of n to the d for all c greater than or for all c lesser than or equal to d. That's the sort of rule here. And that concludes the walkthrough of question 2.
Cool. So for question 3, we're going to explain this in two parts. The first part, I will go through a problem-solving process that you might go through when solving this question, and then I'll walk through the solution. Feel free to skip straight to the solution if you prefer. Okay, yeah, so the process to solving this question. So let's just read the question itself first. So yeah, you're given an array of integers of length n. It's it's decreasing until one element, the value, and after that point it's increasing. This essentially just tells you that it's strictly decreasing before and strictly increasing after. Okay, yeah, so when getting a question like this, very nice thing to do is to start off with an example. And then once you play with an example, it'll give you some intuition about what the question is about. And then you might come up with a brute force solution just to get something to improve upon. Once you get the something to improve upon, you think about how you can do or how you can make it better. So let's look at an example. And it's randomly picked an example where n is the power of 2. So this thing satisfies the properties specified in the question, which is nice. So now let's think of a brute force solution. Well, one obvious thing that comes to mind is why don't we just go through all of the indices, 1 all the way to 8, and then for each index checking if a I is smaller than a I plus 1 and a I minus 1. So basically it's like if this is true, then we're going to return I as the value. So the runtime of this would be O of n because you have n indices to iterate over, and then each one takes O of 1. Okay, so now we ask ourselves, can we do better than linear time? And if we think about this, like what's a better runtime than linear, then it's obviously log. So then we ask the question, what does this mean in terms of like a recursion tree perspective? Well, yeah, basically means that one way to have this is where you have log n levels, where each level does O of 1 work. So something like this, where there are log n nodes, and each node is O of 1 work. And this should remind you of so if we start off with something of size n, then the next one should be like n over 2, next one would be n over 4 until you go to 1. Yeah, so that's an intuition for how the problem should shrink. Yeah, so the idea is that you start off with something of length n, and then you generate a subproblem of length n over 2, and then another subproblem of n over 4, etc. So basically you just keep slicing by half each time. And yeah, so this sounds like a divide and conquer kind of question. So where the recursive call is called on the part that contains the answer, which is like the value. So if we look at our example, so yeah, like it's pretty common to start from the middle as like a marking point that tells us which half to throw away and recurse on. So for this one, the middle element would be 3. And so essentially, you can cut this array in half and then decide which side you can recurse on. So, okay, looking at our example, we can see that the value happens at 2. So this is 1, 2, 3, 6, 7, 8. Okay, well, it happens at index 3 if we're one indexing. And yeah, so this we're treating this thing as the middle element, and we want to decide whether or not we recurse on this side or this side. So the idea is that when there's only one element left, that element should be the value, which means that every time we do a recursive call, the half that is like thrown away cannot contain the value. So for this particular situation, can the value exist on that side of the array? Okay. No, because the value has to like be smaller than something. And if 4 is greater than 3, um, the people on the right can't be a value because like 3 is smaller than them, so they can't be a value. Um, so therefore, that means we're going to recurse on this left side. Okay, so we can kind of see a more general pattern or algorithm condition, I guess, which is that if um, let's say mid element is smaller than right, then it's like recurse on left side, else recurse on the right side. Um, and I suppose it's like recurse and then plus n over 2 because we want to find the index. You want to find j. Yeah, so you just want to find the actual index, not the you just want to find the index. So you plus add this to kind of balance that out. Yeah, so yeah, anyway, so the idea is that you just keep throwing away the part that cannot possibly contain the value. And then so once you just throw away all the parts and you only have one number left, that number has to be the number that's the value. Yeah, so that's the thought process, and then you just formalize this into a solution, 3-part solution. So the algorithm is that, okay, yeah, if you have one element, you just output that element's index, since it's asking for indices. Otherwise, check this condition. If middle is smaller than the thing on the right, that means that means the right half cannot contain the value, and therefore we should recurse on the left half. Otherwise, the right side has to contain the value, and therefore we should recurse on the right side and add n over 2 because we want to find the actual index. When the algorithm is, well, the function, I guess, is called on an array of size 1, then the only possible value is 1, so we just return 1. And now this is kind of reiterating what we had from before. So if the middle number is smaller than the right number, we know that the peak can't be on the side or the half of the array that's on to the right of the middle number, and therefore we're going to recurse on the left side. Yeah, and by induction we're going to assume that the function does what we want it to do, i.e. find the value in that array. And then similarly, if the middle element is greater than the element directly to its right, that means the value in this big array has to be on the right side. Therefore, we're going to recursively call on the right side, and by induction, we're going to assume that the function does what we wrote it to do, and therefore it will find the smallest, or it will find the value on the right side, right half of this original array, and therefore this function will return the index of the value. And we add n over 2, because if it's not in the first half, the left half, that means its index would be n over 2 plus whatever is returned from the right. Okay, runtime, well, the subproblem gets halved every single recursive call, and each recursive call only does an if check, which is O1, so then it's O1 times log n, so therefore it's O of log n.
Hey everyone, welcome to the fourth problem on the discussion worksheet, merge sort. In this problem, we'll be going into grueling detail to find the runtime of what should be a highly familiar algorithm from CS61B. I won't be covering the algorithm itself in too much detail, but recall that merge sort takes in an unsorted array and returns a sorted copy of it. Now, the way that it does this is by breaking up the input array into halves all the way until we get just a collection of singleton arrays, or maybe some number of empty arrays as well. And so empty arrays and singleton arrays are both sorted by default. So now we go back up the recursion tree and repeatedly call merge on adjacent pairs of arrays until we merge to a sorted copy of the original output all the way at the bottom. So if this quick overview just reminded you how much you've forgotten about 61B, I highly encourage you to pause this video right now and to go back through this algorithm in the code before continuing to the next part of this video. So in part A, we're interested in T of n. T of n. So what is T of n? T of n is a function on the length of the input array, and we're interested in the total number of operations in this entire algorithm. We are recursing on the size of the input array, so the base cases are when the array is of size 0 or 1. So T0 and T1. In either of these cases, we're essentially doing nothing, because if we have a singleton or an empty array, they're sorted by default, so we just have to return the input itself. So since we're doing no work at all, it's constant time, so O of 1. So this is the base case. Now for the recursion, we look at the code. In this code, we're breaking up the original array into two sections, one called left and one called right. So this is, from 1 to the midpoint, and from midpoint to the end. We're breaking them up and sorting each side. So we're calling merge sort on each of these halves. What this means is we get two subproblems, two subroutines, each of size n over 2. n over 2, again, to remind you, is the length of our input. So this is the recursive part of the work that we have to do. What about the non-recursive part? The non-recursive part, we see that we're calling merge on the result of these merge sort operations, L and R. So what's the runtime of merge? On a high level, merge takes two pointers through A and B respectively, and you keep adding the next smallest element from A or B. So what this tells us is that each element in A and in B is processed and copied into C exactly once. So the runtime T of just the helper merge, given inputs of size A and B, I'm using A and B so not to confuse you with the M and N here, not to confuse this M and N with this N. Given two inputs of size A and B, the runtime is O of A plus B. So in this particular instance, when we're calling merge on L and R are each of length n over 2. So we get O of n over 2 plus n over 2, which is just n. So this is our recursion. For part B, we'll go into the grueling detail of the runtime analysis. There is an algebraic way to do this in a more intuitive way. The algebraic way is outlined very much in detail in the solutions, but I'll give sort of the more intuitive way here. So we see that from the previous part, we had t of n equals 2 t of n over 2 plus a linear term. We can keep writing t of n over 2 in terms of t of n over 4, in terms of t of n over 8, so on and so forth, and eventually we'll get to t of 1, which where we'll be doing no work. So essentially, we just have to count up all the non-recursive work that we're doing on each level and add them all up, right? So on this level, we're doing, well, this level is the t of n level. We're doing n amount of work, right? Because this is the non-recursive work. And at this level, we're doing t of n over 2. There are 2 subroutines, each of which is of size n over 2. So the non-recursive work we're doing is proportional to the size of the input. So this is 2 times, 2 is the number of problems, and n over 2 comes from this right here. All right, so this is also n. In the next level, we have 4 subproblems, 4 subroutines, each of which will be t of n over 4. Okay, so the non-recursive work we're doing is 4 times n over 4, which is also n. So you might be seeing a pattern here. At each level, we're doing n work, but how many levels are there? So this is equivalent to asking, how many times do I need to divide an array in half until I get to singletons? So this is precisely log n times. You can see this by saying, well, you know, how many times, right? So how many times do I need to divide by 2 repeatedly so I get down to 1? This is log of n. So there are log of n levels, and at each level we're doing n work. So we have n log n as the runtime of our program, merge sort. So again, this is a little bit hand wavy in terms of saying, you know, we only care about the non-recursive work because the recursive work is accounted for in the next step and the next step and the next step. But the idea is that at each level, the merging is going to take n work, and there are log n levels. If you want a more rigorous proof of this, you can see this in the discussion solutions. All right. So for parts C and D, we're interested in the proof of correctness of merge sort. Let's look at part C first. Part C deals with the helper function merge. We're asking, what do we want out of merge? So what properties do we want for the output of merge? If we look at the function merge sort, the final return statement, you know, the end all be all, the thing that's supposed to give us our sorted copy of our input, is a function call to merge. So I better know that the output of merge is a sorted union of its input arrays. There are two things that are of note here. One is that it has to be sorted because, you know, we want merge sort to actually end up being sorted. And then the other is union. We want all the elements that were originally in A, or all the elements that were originally in L and R, to also end up in the return statement of merge. Okay, so this is the desired output, and the input, we need to have 2 sorted arrays. So when we input array A and array B, I better know that A and B are sorted because we're taking a pointer through A and B, stepping through and adding in the smaller one each time. So this is not a very rigorous proof, but the way to rigorously prove this is by using invariance. The idea is that you want to show that at each step, every time you insert a new element into the array C, the new element is at least as big as the one that has been previously inserted, and it's going to be smaller than everything else that comes after. Okay. So again, you should convince yourself that this invariant is held. All right. So now that we've done part C, we can take merge as a helper function or even as a black box. Basically, we know that it takes in two sorted arrays and outputs a sorted union of those two arrays. So now we're on to part D, and we're going to use strong induction. So for strong induction, we must prove two base cases first. So P of 0 and P of 1. What does P mean? What is P of anything? So P of K in general is a statement stating that if I input an array of length K into my function merge sort, the function merge sort will sort it correctly. So this means we're doing strong induction on the size of our input array. Okay. So we first want to check two base cases 0 and 1, and then we want to say that if everything works up to length, say K, then this also implies length K plus 1 works. All right, so these are our two steps. All right, the base cases are very easy to check because P of 0 and P of 1 both belong in the base case of our recursion when we looked at it in part A. In both cases, we're just returning the original array, we're doing no work, and merge sort is automatically correct. So we've checked that P of 0 and P of 1 indeed works, so check. All right, now we assume that P of 0, P of 1, all the way up to P of K all are true, which means that merge sort can successfully sort arrays up to length K. And now we want to say that if we give it something of length K plus 1, it'll also return a sorted output. Okay, so we go to the function merge sort, and we see that the first thing that we do after the sort of checking for base cases is we break it up into two sections. We break the input array into a left side from 1 to the middle and a right side from middle plus 1 all the way to the end. Both of these arrays have length smaller than K plus 1. Both of them belong in this section, the section where we assume merge sort actually works. So once we call merge sort on them, I'm guaranteed that both L and R are in fact sorted copies of like 1/2 of our input array. Okay, so now we know L and R are sorted by our induction hypothesis right here. Once L and R are sorted, we finally call merge on L and R. So again, recall that L and R contain all the elements of A together. And so once I merge them, I am guaranteed to get an output with the sorted union of L and R. So the sorted union of L and R is in fact a sorted version of A. So we output sorted A, call it A prime, which means that the statement in fact works. So again, just to recap, we assume that a merge sort is able to sort any array of length 0 to length K, and we just showed that if we put in something of length K plus 1, it'll also work. So by strong induction, we know that for all n in the natural numbers, so for any length, P of n is true. So we now know that merge sort works for any arbitrary length of input. And that concludes question 4.
All right, let's talk about medians. Okay, yeah, so our motivating question is, given a list of numbers that are not sorted, what's the fastest way to find the median? What do you think? Well, naively, we might think, well, we can just sort the array or sort the list and take out the median. And yeah, that works. Runtime would be O n log n. So the natural question is to ask, can we do better than this? It turns out, yes, we are able to do better. And the way to do better is to actually work on a more powerful version, which is the selection problem. But it turns out if we just naively implement a selection algorithm, it won't work. So this question will take us through this process and seeing how we can find the median of an array faster than O of n log n. Okay, so yeah, this begins by describing to us a naive quick select algorithm for finding the kth smallest element in an unsorted array A. Essentially, it picks an arbitrary pivot P, partitions the array into 3 pieces. So if you have an array here, you randomly choose an arbitrary pivot P, and then you split it up or partition it into 3 arrays where the middle array is equal to P, and then the next array is elements greater and then elements smaller than B. And then, yeah, as a quick summary of what quick select does, it picks a random element. Okay, I just wrote it out in bullet point form. And okay, cool. So the question is, if you have an array A, what's the worst case runtime of quick selecting the n over 2th smallest element? Construct a sequence of bad pivot choices. So if we just consider A, we can come up with a sequence that looks like 1, 2, 3, n over 2 minus 1. And this is pretty bad because like every time you do your recursive call, the subproblem only decreases by size 1. So you begin with A, which is size n, and then when your pivot is equal to 1, your subproblem becomes size n minus 1, because you would be doing your recursive call on this portion of the array, which is size n minus 1. N minus 1, and then, yeah, when your pivot is 2, the subproblem becomes size n minus 2, etc., until your size problem is size around n over 2. Something like this. And then, yeah, so when your subproblem is size n, let's think about how, like, the amount of work that needs to be done in the partitioning stage. So in order to partition an array of size n, you need to, like, against a pivot, say pivot is like, I don't know, 1, you need to iterate through the entire array and then compare with the pivot to determine which bucket the element you're currently at should go into. So, like, if it's size n array, then you need to do n comparisons. Like, yeah. So that means when your subproblem is size n, you need to do O of n work. This, you do like O of n minus 1 work, or like, okay, I'm not going to write O of n minus 1 because that's weird. So I'm just going to say it's n work and then n minus 1 work. And it's n over 2 work. So total work you need to do on this sequence of bad pivot choices would be n plus n minus 1 plus n over 2. And this is, well, this is O of n squared. Yeah. Yeah, so that's the worst case runtime. I guess you could have a even worse pivot selection choice, which is you pick pivot 1, 2, 3, n over 2 minus 1, and then you pick pivot n minus 1, n minus 2, n over 2 plus 1. That'll be an even worse case. Well, this would be the worst case, but asymptotically, it's still quadratic. Can we do better? And yeah, this is what part B gets us to come up with. It defines a new algorithm, better quick select, that basically just picks a better pivot. And it picks a better pivot using the median of median strategy. So if you were to write what better quick select does in bullet point form, what would be the 3 things that it does? Yeah, no, that's quick select, and this is better quick select. So rather than using a random pivot P, we pick a good pivot P using the median of medians algorithm, and then we basically do the same thing as quick select. So here's the median of medians algorithm. So I guess I can step through this roughly. So if we have an array A of length n, so step 1 is we group the array into elements, into 5 element groups. 4, 34, blah, 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 4. Okay, so I'm just going to call this array A1, A2, A, n over 5. And step 2 is find the median of each group. So I'm going to find the median. I'm going to call it M1, M2, M, and floor div 5. These are the individual medians, and then we're going to create a new array with these medians. I guess you can call it M is equal to M1, M, N over 5. Okay, so this new array, and then we find the true median using better quick select. So this is like a nested recursive call. So then find median using better quick select. Yeah, so it's like interesting how better quick select relies on median of medians, but then median of medians also relies on better quick select, which is pretty cool. So let's go into the problem. Yeah, so the problem is let P be a chosen pivot using the median of medians algorithm. And we want to show that a certain number of elements, P is greater than them, and P is also smaller than a certain number of elements. So here's the algorithm for reference. And now I suppose let's draw this thing again. A is equal to this guy, length n. And then you're going to have a bunch of small arrays, A2, over 2. We'll have medians, M1. Okay, and then we're going to pick the median of the medians, P. Okay, so now we can bound the number of elements that P has to be greater or equal to. So, okay, I guess for P is greater or equal to X for at least 3n over 10 elements. Do this part first, because the other part is symmetrical. So because P is the median, so P is median of, I guess, let's call the big set M1, M, n over 2. Is median of M, therefore P must be greater or equal to n over 5. okay, so P is greater or equal to M for this number elements. So i.e. P must be greater than half of the people in the array M because it's the median. Okay, so now, yeah, so so each of the medians themselves, so each median Mi is greater or equal to at least, so okay, yeah, it's greater than or equal to 2 elements in its group. So therefore, P is greater or equal to M for n over 5 times 1/2 plus 5 times 1/2 half times 2, because so these are like the original medians in M, and these are talking about the numbers that are smaller than the corresponding median and the original group. So then if you add these together, it is 3n over 10. Yeah, I guess you have floor division, but it's basically this. Okay, and then the other argument for P is smaller or equal to X for greater or equal to 3n over 10 elements. This is the same argument except in reverse. I won't write it out, but the idea is basically the same. So P has to be smaller or equal to n divided by 5 floor division times 1/2 elements, because it is the median of the array M. And then each median within that array is smaller or equal to 2 elements, not including itself. And then you just add those numbers together, and then you get 3n divided by 10. Cool, so this better quick select algorithm turns out to be better in that it can find the median in linear time. So in this question, we'll prove that fact. So to remind ourselves, what exactly is better quick select? Next. Yeah, so we first pick a good pivot using the median of medians algorithm, then we partition A into 3 pieces, and then we recursively call. Cool. So yeah, let's just come up with a recurrence relation for T of n, where T of n is the runtime of better quick select when A is size n. So T of n is equal to, okay, yeah, so pick a good pivot. So partitioning A into 3 pieces using P, that takes linear time once we've chosen the pivot, because to partition, we need to look at every single element in A and then decide which bucket it fits into. Okay, now next, we invoke the median of medians algorithm. Well, okay, first of all, we know that the subproblem generated by the median of medians algorithm has at most 7n over 10 elements by the medians of medians algorithm and the thing that we proved in part B. So our subproblem is size this. we call beta quick select on an array A that has at most size 7n over 10. So now we need to figure out how long the median of medians algorithm takes. So grouping the array into this, that should take like linear time, I guess. Or do you even need linear time? I guess, yeah, sure, something like linear time. And then to find the median of the 5 elements is constant time. And then we have, so it's like n floor div 5 times constant time. So that's that step. Creating a new array, sure. And then we do finding a true median of an array of size n over 5. So that's t of size n over 5. Parentheses. I guess you can just add some random linear time thing. But we can, because we're doing asymptotic analysis, we can kind of just group these two guys together. So we'll do that. So yeah, so this would be the recurrence relation. This thing. Oh, I guess like asymptotic analysis, so we group these things together. Cool, so now we want to, that's a very spread out equation. We want to show that this holds for some C. And the way we do this is actually pretty clever. Now we want to show that this, we want to show that this is true. Okay, so it says, hint, using the master theorem will not work here. Find recurrence relation and try to use induction to show that that's true. Okay, so let's use induction. So I guess base case. So induction is proving something about something for all n. So base case, when n is equal to 1, check if it's true, is t of 1 smaller or equal to c for some c? Well, yeah, it's just when the size of the array is 1, then you just take its constant time operation. So base case holds, and then the inductive hypothesis is that assume, I think we can use strong induction here because we're dealing with elements that are not just one size smaller than us. So inductive hypothesis, assume the claim is true for all n smaller or equal to k. Okay, and then inductive step, consider n is equal to k plus 1, I guess. Okay, and actually let's do it like this. So assume that the claim is true for m smaller or equal to n minus 1. And now consider when m is equal to n. So i.e., so if the claim is true for m smaller or equal to n minus 1, that means for all m that's smaller or equal to n minus 1, there exists some c such that t of m is smaller or equal to cm. Okay, so now let's consider when m is equal to that. So t of m, our thing we have above tells us we have this plus t m over 5 plus O of m. Okay. And I suppose for convenience, we can replace O of n with d of n. just to give it a more concrete value to work with. So then we would have T of M plus M. Okay, so we can, using the inductive hypothesis, we can replace some of these T's. So T of M is equal to C, 7M divided by 10, plus C, M divided by 5, plus D of M. Okay, and this is equal to something like okay, I don't know why I use M here. This should be N. N, 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 N. Actually, it doesn't really matter, but whatever. N, D of N, I think. Okay, so basically we want to show that this is smaller or equal to Cn for some C. So we want this to be smaller or equal to Cn. So then we can find out what the actual value of C should be. So then we can group terms together. So we have C, let's see, divided by 10 plus, so 2n over 10 minus 10 over 10 n, smaller or equal to negative dn. And then we have C. Okay, so what is this guy? We have, okay, negative 1 over 10 n, smaller or equal to negative dn. Therefore, cancel out the n's. We just have C is greater or equal to 10d. So then we can just take C is equal to 10d. And then we're done.